Hello, Precalc C. We were slightly short, like say 10 minutes from finishing everything we had to learn today. These half days are killing us. We got to move on. So I'm just going to do this now. You're going to watch this video. Here we go. Today in class we learned the new definition of the conic sections, which is that given a focus, single focus, and a single directrix, the conic is the locus of points with constant eccentricity. And we did a couple practice problems, or one practice problem basically, and now it's time to sort of bring it all together and to unify the two definitions. So here we go. What I want to do right now is to find all relationships between A, B, C, D, E, and basically everything, even P, for an ellipse. Okay, and so what I want to now do is draw a generic. I'll explain. I'll explain. What I want to now do is to draw a generic ellipse using the new definition of ellipse. So the new definition of ellipse says that an ellipse is made by finding all the points with constant eccentricity less than 1 for a given focus and a given directrix. So here is my focus, here is my directrix, and I guess these points should be closer to the focus than the directrix. Maybe make this directrix a little bit farther away. Okay, great. Oh, the other one here is D, which is the Directrix Distance. Okay, so what am I doing? I am adopting the new definition of conic sections, the one that we just learned today, and from that I want to prove all things. Okay, so let's set up our coordinate system in the same way that we did before, where the center of our coordinate system or the origin of our coordinate system is at the center of the ellipse. And let's once again call this point C. So I'm still going to use C to refer to the distance from the center to a focus. I'm still going to use A to refer to the distance from the center to a vertex. And I have a new E is eccentricity. B is still B. But now I have a new thing, and the new thing is D. D is the so-called Directrix Distance. It is the distance, the directrix is from the center. So since I established the coordinate system here at 0, 0, it means that the equation of this directrix is x equals D. It's D away from the center. Okay, good. And from this setup, using the new definition of the conic sections only, I want to derive all the various relationships between all these things. Okay, let's go. I can use only, and this over here is negative A0. Okay, I can use only the new definition of the conic section. So the new definition says that any point is on the ellipse if it satisfies that ratio definition. So I think we should take the point A comma 0 because that's one of the points which I know to be on the ellipse. And what can I say about this point A comma 0? Well, I know that if I take the distance to the focus over the distance to the directrix, then that has to be the eccentricity. Okay, and well, what is this distance? It's A minus C. And what is this distance? It's D, the distance to the directrix, minus A. And so immediately I get one equation, which is distance to focus, A minus C, over distance to directrix, D minus A equals E, the eccentricity. And then I have another fact. Let's see, I'll use purple, which is that, or rather, I can repeat this same move for the other points which I know to be on the ellipse, which is this point here at negative A0. And so now I'm going to take the distance to the focus. Here, the distance from this point to the focus is A plus C. And the distance to the directrix, this is going to be quite a big distance. That's going to be A plus D. And so from this I get my other equation, which is that A plus C over A plus D also has to be E the eccentricity. Right, from these two equations, I can figure out all the relationships between A, C, D, and E. In particular, if I now multiply by these denominators to get rid of them, I get A minus C equals ED minus EA. And over here, I'm going to get A plus C equals ED plus EA. And these two equations are very similar to each other, and in fact, they are sort of begging to be added. If you add these two equations together, then what you get is that 2A equals ED. No, 2ED. This is very exciting because it means that A is ED, and this is not something I knew before, and something that's not obvious at all, which is that the eccentricity of an ellipse, this mysterious ratio which defines the ellipse, is A over D. It's the distance from the center to a vertex over the distance from the center to a directrix. Okay, but there is another option with these two equations. I could subtract them. If I instead subtract these two equations, then I get a different, okay, well let's just do it, right? If I upside down subtract, or if I just regular subtract, A minus C minus A plus C is negative 2C, and ED minus EA minus ED plus EA is negative 2EA. And so C is EA, and so eccentricity is C over A. Okay, now you might say that that's something that we knew already, but previously, before today, we had simply defined eccentricity as C over A. But today, I defined eccentricity differently, and it wasn't clear until this moment that this new thing I was calling eccentricity today is actually the same as the thing I was calling eccentricity previously, but now we have in fact shown that this sort of old eccentricity equals new eccentricity, so to speak. Okay, a couple more things. These two equations together can be set equal to each other, and we can get that A over D equals C over A, and so in fact A squared equals CD, and so that's actually kind of interesting. If I divide by C, I get that D is A squared over C. And the kinds of ways we've been manipulating ellipses up to this point, we often know what A, B, and C are for any ellipse. Now this gives us a formula for D, the directrix distance, in terms of A and C. Okay, so if I know how far the vertex is from the center, and I know how far the focus is from the center, this formula will actually tell me where my directrix is if I didn't know to begin with. Okay, so I have I have this formula, this formula, this formula. There's even one more step we can do here, which is we can use the one other point that's kind of floating around here, this point 0b. What can I say about this point? Well, it too must also be on the ellipse, and therefore must satisfy the definition of the ellipse. And so, what is the definition? Well, the distance to the focus over the distance to the directrix has to be E, the eccentricity. And so if I take what is the distance from this point to the directrix, well, it's D. What's the distance to the focus? I'm not sure. Let's temporarily call that like X or something. And then what do I learn by applying the definition? I learn that from that point 0b, the distance to the focus, which is x, over the distance to the directrix is E, the eccentricity. But that means that x has to be ED. And we've just seen a minute ago that A is ED. And so we conclude that x is in fact A. This is a direct proof using the new definition of ellipse only, that this segment here has length A. And if this segment has length A, and this segment here has length C, and this segment here has length B, then this proves the Pythagorean relationship that b squared plus c squared equals a squared for an ellipse, based on this, this new definition of ellipse. So that's nice. Okay, last thing is let's calculate the length of the lattice rectum. This picture is getting a little complicated here. Let's do that using, once again, the new definition of the conic sections only. So if this is the lattice rectum, which is perpendicular, and this has length L, then what can I say about that point? Distance to the focus over the distance to the directrix is E, the eccentricity. And so, what is the distance from that point at the end point of the lattice rectum to the focus? Well, it's just L, and the distance to the directrix is, this distance is D minus C. And so, I can tell you that the distance to the focus, L, over the distance to the directrix, D minus C, equals E, the eccentricity. And so, I conclude that L is ED minus EC, and I think this can now be manipulated. Let's see, how do I want to do this? ED is just A, so this tells me that L is A minus, and in place of E, I'll just write C over A, because I know that that's true now. And so, this is, if I get a common denominator, then that's A squared minus C squared over A, but then I also know that A squared minus C squared is B squared. And so that is a direct proof of the length of half of the lattice rectum based on the new definition of the ellipses only. Okay, so this tells you everything you would need to know about the relationship between A, B, C, D, and E. And for homework, you are going to determine the same kinds of relationships for a hyperbola.